Okay, so here is a problem that I made up. Let me explain the problem and then go through the steps of how to solve this problem. I have two electric charges. I call this Q1 and Q2, and they're both on the x-axis. And Q1 is at the origin, Q2 is 4 centimeters, 0.04 meters away. And what we want to do is to find the electric field at this point over here on the y-axis, 0.02 meters that way. And I just picked a problem just to practice these kind of things, but so let's just get started. Oh, and I do have this. Q1 is 3 nanocoulombs, Q2 is negative 5 nanocoulombs. Okay. So the first thing we need to remember is that the electric field due to a point charge, let's say that we have some positive charge right here. The electric field points away from it because it's positive. And if I have some vector location, I'll call it R. If I know the vector from the point charge to where I want to find the electric field, I can use the following equation. The electric field vector is K times Q over the magnitude of R squared R hat. Now that may look weird. A lot of times textbooks will write it as just E, K, Q over R squared. That is the scalar version. And that's fine if you only have one electric field. But the problem is that I have two electric fields and I have to add them together at this point as vectors. So let's just sketch what this electric field looks like right here. So right here I have Q1 and it's going to create an electric field pointing away up here. So I'll write it. I shouldn't have put that Y there. You know, the Y is just going to have to suffer. It's just the price of progress. So that's E1. That's the electric field due to point 1 at that place. It's pointing away from it. Now for this one, it's a negative charge, and it's going to be pointing towards it. So negative charges have electric fields that point towards it. And so towards it is this way. So this will be going, and don't worry about the magnitude right now, so I have that, E2. So then the resultant vector, the total electric field, E, is going to be E1 plus E2. And so I have to add these as vectors. And so if I just use this to find the electric field due to Q1 and electric field due to Q2, I don't know how to add these two vectors, right? Because I don't know what directions are going, and direction does matter. So we can see that this would probably be something like that, but we need to find them as vectors. If I use this form, I get a vector value for each electric field. So here's what we're going to do. You find the vector from the charge to the observation location. I'm just calling it R for right now, and that's that vector right there. I need to find this R hat. R hat is a unit vector pointing in the direction of R. So we can define R hat as the vector R divided by the magnitude of the vector R, and that will give us a vector. So then when I take the magnitude of the vector, it's a scalar and I can square it, but then I multiply by this R hat and I get a vector again. Okay, so I know that seems crazy, but let's just do one thing at a time. Let's just find the electric field due to charge 1 at that location. And I'm going to do this step by step, and then we're going to do the exact same thing for Q2, and then we'll add them together. Okay, so step 1, I'm going to just draw Q1 and that observation location. Okay, so here is my axis. There's Q1. I don't care about Q2. I don't care about it at all. There's my observation location. There's nothing there. I just want to find the electric field there. So let's call this vector R1. It's the vector from charge 1 to the observation location. So since Q1 is at the origin, and this is 0.02 meters up, then I can write this as a vector. So I can say R1 is the vector 0.020 meters. So I'm using this ordered pair version of a vector. You could write it like this too. R1 equals 0 x hat plus 0.02 y hat meters. That's the same thing. I like that notation. So once I have r, I need to now find the magnitude of r. So let's find the magnitude of r. You can find the magnitude of a vector. I'll write it like this. R1 magnitude is going to be the square root of the x component squared plus the y component squared plus the z component squared. So the x component of this vector is 0. So write that as 0 squared plus the y component, which is 0.02 squared plus the z component, 0 squared. So I get 0 squared plus 0.02 squared plus 0 squared equals the square root of 0.02 squared. But if I take the square root of a square, I just get 0.02 meters. So this one actually is pretty easy, and I did it the full way so you can see how it's done. Since the vector's in just the y direction, the y component is the magnitude. Okay, so that's the magnitude of the vector. Don't confuse that with the actual vector. Now I can find, the next thing I want to do is to find r hat. So r1 hat, the unit vector, is going to be the vector r1. So it's 0, 0.02, 0, I'm going to leave off the units for now, divided by the magnitude 0.02. And so if I take a vector and divide by a scalar, I need to divide each component by that scalar. So this is going to be the vector 0 divided by 0.02, 0.02 divided by 0.02, and 0 divided by 0.02. So 0 divided by 0.2 is 0, 0.2 divided by 0.2 is 1, and 0 is 0. So I get 0, 1, 0. And that is equal to r1 hat. So that's the direction of r1, which says in the y direction, which we knew, but I wanted to do it the full way so you can see how to do it for other situations. Now, one of the other important things, there's two important things about unit vectors. The first is that they have to have a magnitude of 1. So if I look at this, if I take the magnitude of this vector, it'll be the square root of 0 squared plus 1 squared plus 0 squared, which is 1, so that is true. And also it have no units. I know it's called a unit vector, but it has no units. And this vector up here has units of meters, and the magnitude has meters, so the meters actually cancel, and it does have no units, so check. That's a thumbs up. That worked. Okay, so I have I have r1 hat, I have r1. I can now put in my equation. So let's write down E1 is K Q1 R1 hat over the magnitude of R1 squared. I forgot to say K is a constant. Let me put it up here. K equals, also it's sometimes written as 1 over 4 pi epsilon naught. This is a different way to write it. And it's 9 times 10 to the 9th Newton meter squared per coulomb squared. So we have everything to put in here. Let's do that. E1 equals K 9 times 10 to the 9th. I'm going to leave off the units. Q1 was, what was Q1? 3 nanocoulombs. So that's 3 times 10 to the negative 9. Now I have R1 hat, which is right here. 0, 1, 0. And I need to divide by R1 magnitude squared. Well, R1 magnitude is 0.02. So I'm going to say 0.02 squared. So these are all the scalar values. Let's do these first, and then we'll just leave that as a unit vector. So I'm going to pull out my little calculator. I like this. This is the one I like just because it's cheap. Now right here, you could enter 9 times 10 to the 9th times 3 times 10 to the negative 9th, and I'll do that. But you could also say, well, I have 10 to the 9th and 10 to the negative 9th. That's going to be just 1. So you just need to do 9 times 3, which is not too hard to do. Okay, but let's do it the full way. You don't have to use parentheses, okay? Get to know your calculator and be familiar with it. So in this case, I don't need to use parentheses up here if I use the scientific notation button. I wouldn't use 9 times 10 to the 9th. I would do this. 9. Can you see that? Let's see, put it right here. No, right there. 9. And then I'm going to use the scientific notation button, which is, I'm not really good with calculators. I don't like calculators, but EE. So I'll do second EE 9. Okay. That's 9 times 10 to the 9th. Now I can say times. It's going to treat that all as one number. Now I'm going to say 3 times 10 to the negative 9. So you got to use this negative sign, not the minus sign. So I'm going to use negative 9 right there. Now I need to divide by 0.02 squared. So I can say divide 0.02 squared, and that's it. And so it's okay if you, I don't have to put parentheses down here either, because it's going to take the square first. It's going to do that order of operation first. It's just a higher order operation, so it does that. So and then it'll do from left to right. So I get 6.575 times 10 to the 4th. 6.75 times 10 to the 4th. And then I have that vector 0, 1, 0. And that's going to be newtons per coulomb. Now, I could write that as, I could multiply this out. And I could get 6.75 times 10 to the 4th, 0 newtons per coulomb. And that's E1. Okay, so now I know the magnitude of the electric field right there due to that charge. Let me just check. 9 times 3 is 27 divided by 0.04, 27. Okay, it seems okay. I'm just making sure I got the right answer. Okay, so now let's do the exact same thing. Let's do the exact same thing for charge Q2. I'm going to draw it right here. So here's Q2. And the first thing I need is the vector R2. So there's more than one way to do this, but I can go ahead and see R2. If I start from here and I want to end up there, I'm going to go negative 0.04 in the x direction, and then I'm going to go 0.02 in the y direction. So R2 is going to be negative 0.04, 0.020 meters. Okay, so that's important. But other than that, I'm going to use the same procedure. So let me write down the procedure. So I'm going to write down this. E2 equals K Q2 over the magnitude of R2 squared R2 hat. And so the steps are going to be, number 1, find R2. We did that already. 2, find the magnitude of R2. 3, find the unit vector R2 hat, which is going to be R2 divided by R2 magnitude. 4, find E2, right? Because once I have the magnitude to go in there and I have the unit vector to go in there, I can do everything. And so we already said R2 was equal to the vector negative 0.04, 0.020 meters. So let's find the magnitude. R2 magnitude is going to be the square root of this squared. Okay, so there is a negative sign there, but if I square it, it doesn't really matter. So I'm just going to write this as 0.04 squared plus this squared, 0.02 squared plus 0 squared. You could probably do this in your head, but I'm going to go ahead and use the calculator. Okay, so I'm going to clear. I'm going to say the square root, which is, there's my square button, so it's over the square root, or the square root over the square root, and I already put the parentheses in there. 0.04 squared, and I don't need to put parentheses around that, plus 0.02 squared, and then close parentheses to end the square root. And I left off the 0 because 0 squared is 0 right there. And I get 4.47 times 10 to the negative 2 meters. And so you'll notice that the magnitude should be greater than either of these two, but less than the sum of them. So it should be less than 0.06, but greater than 0.04. Okay, which it is. That's 0.0447. Okay, so now I need to find R2 hat. R2 hat is going to be equal to R2, which is that, negative 0.04, 0.020 meters, divided by the magnitude, 0.047 meters. That's 10 to the negative 2. And then to do that, I can just take each component and divide by this. So I'm going to get negative 0.04 divided by 0.047. I'm going to leave off the negative sign because I know it's negative. So I'm just going to say 0.04 divided by 0.047. And I get, and I did round, and that's okay. So I get 0.8, this times 10, see it's 8.5 times 10 to the negative 1. So I'm going to write that as negative 0.85. Now let's do the same thing for the 0.2. I'm going to take 0.2 divided by that. So I'm going to say 0.02 divided by 0.047. And I get, what's that? 0.4. So again, it's times 10 to the negative 1. I apologize for my glariness. So it's 0.426. Let's say 0.426. And then 0 divided by that is 0. So that's my unit vector. So I found R, I found the magnitude of R, I found this. Now I can go ahead and plug in and find E2. So E2 is going to be K, which is 9 times 10 to the 9th, times Q, which is, notice that I didn't take into account the direction of the electric field due to the charge, because that's in the charge. The charge was it negative 5? Negative 5 nanocoulombs. So negative 5 times 10 to the negative 9th coulombs. And then I need to multiply by this unit vector, negative 0.85, 0.426, 0. And then I need to divide by the magnitude squared, so I have this number squared. So I'll say 0.047 squared. So this is just a scalar value. I'm going to do that first, and then I'll multiply it out here. Okay. Now I'm going to use the trick. I know it's negative because that's negative. And I have 9 times 5 is 45. And then 10 to the 9th times 10 to the negative 9th is 1. So this whole thing on the top is negative 45. So let's do negative 45 divided by that squared. So that just saves me a little time. So I'm going to leave off the negative. 45 divided by 0.047 squared equals. And I get 2.04 times 10 to the 4th. So I have 2.04 times 10 to the 4th. And that's negative. And then I have multiplied by this. Negative 0.85, 0.426, 0. Now I can multiply this scalar value by these to get a single vector. So I get E2 equals, so here I have a negative times a negative, so that's going to give a positive, which if we think about it, it's correct, right? I'll go back to the picture, but that should be positive. So I'm going to multiply that. I already have that number in there. So I can say times 0.85, and I get 1.73 times 10 to the 4th. And then I'm going to multiply that by 0.426. So say clear 2.04. I'm going to leave off the scientific note. Well, I'll include it. E to the 4th times 0.426 equals, and I get 8.7 times 10 to the 3rd. 8.7 negative times 10 to the 3rd. It's negative because that had a negative number. I bring it in, multiply by positive, I get a negative. And then multiply that by 0, I get 0 newtons per coulomb. And so let's just switch back over here and make sure those. So I have a positive x component and a negative y component. If you look back over here, that's what we said, right? We said here's E2. It's going in the positive x direction, but it's in the negative y direction. So that's cool. Now I'm going to write here E1, which we already had. 675. So it's 6.75 times 10 to the 4th, 0 newtons per coulomb. So there's my two electric field vectors. I spaced it out so it looked right. And then to find the total E, I just add those together. So E is going to be the sum of these two vectors. And to add vectors, I add the components. So I'm going to add the x and the x. So that's this plus 0. That's pretty easy. 1.73 times 10 to the 4th. Now this one, let's do that in the calculator. Clear. I'm just going to take this, subtracting that. It makes it a little bit easier. 6.75 times 10 to the fourth minus 8.7 times 10 to the third. And I get 5.8 . Yeah, okay. 5.8 times 5.88. 5.88 times 10 to the fourth. And then I get 0 minus 0 is 0. And that's my answer. Okay, so now let's just do one more thing. Sometimes you want to find the magnitude of that electric field. So I can do that. Just take the square root of this squared plus this squared. Now I can actually factor out the 10 to the fourth. And then I'm going to square 10 to the fourth and take the square root of 10 to the fourth. So it's going to be 10 to the fourth. So I don't have to put that in my calculator. I'm just going to do these squared. So I'm going to say clear square root 1.73 squared plus 5.88 squared, close parentheses, enter. And I get 6.13, and then I still have that times 10 to the fourth newtons per coulomb. So that's the total electric field. This is the best answer, but sometimes you may want it as just a magnitude. Okay, so let's just go back to the original picture for a second. So what we did is to find the electric field due to each point charge. And to find the electric field due to each point charge, you need the vector from that point charge to the observation location. And so I got those two. I need to find the magnitude of those vectors and the unit vectors. And so just think back, if I just used this equation, once I found that the magnitude of E1 and E1 and E2, how would you add them together? You wouldn't know if you don't know the directions. And so that's what makes it really difficult. But this is the way you'd want to do it. And it doesn't matter if there's 2 charges or 3 charges or 10 charges, you'd use the same idea. Okay, I hope that helps.